All right, so continuing on here, guys, from Friday. Okay, the big thing here about kinetic energy, guys, is it's related to two things. Okay, two things can affect the amount of kinetic energy that an object has: its mass and its speed. Okay, it is possible for something very small to have the same kinetic energy as something much, much larger, provided the small object is moving very fast. Okay, everybody with me there? For example, it is possible, okay, for, let's say, a brick to have the same amount of kinetic energy as a truck. The brick just has to be moving a lot faster than the truck. Okay, everybody follow? All right, so those are the two things that can affect, okay, the kinetic energy of an object. All right, so any moving object has kinetic energy. When a solid object moves, we consider all of its particles to be moving in unison. All right. Right now, all the air particles in this room are also moving. Okay, but are they moving in unison? No, they're all moving randomly. Now, were I to open a window, would more of them be moving in unison? Would you feel that? Yeah, okay, right now you don't feel all the little air molecules hitting you because, well, they're all hitting you from different directions and they're all hitting you in different places, okay? So you don't notice it, thankfully, because it would probably drive you insane if you did, okay? But when it gets windy and big, large collections of air molecules that now have considerable mass because they're all together start moving in the same direction, you do feel it, okay? All right, so even when molecules are not physically attached to each other, they can still move together, okay, like they can with wind. All right, so we call this mechanical kinetic energy. The air molecules in this room right now that are moving randomly have thermal kinetic energy. All right, their movement would slow as they cool, okay, or increase as they were to heat up. All right, now if I'm looking at this roller coaster here, and we'll talk more about roller coasters in another lesson, but up here at the highest point, I would have very little kinetic energy. But down here at the lowest point, I'd have a lot more. Wouldn't I be going fastest here at the lowest point on the track? Okay, so on a roller coaster, your amount of kinetic energy changes, and it's very high near the bottom's cam and very low near the top, because here up at the top, you're not moving very fast. Now, if I'm talking about my total amount of energy, both potential and kinetic, okay, is my total amount of energy here different than it is here in the perfect physical world? The answer is no. Remember, energy can't be created and it can't be destroyed. So in the perfect physical world, you have the same amount of total mechanical energy at the top of the roller coaster as you do at the bottom. The difference is how much of it is potential and how much of it is kinetic. Okay? Up here, I would have mostly potential because I'm not moving very fast, but I'm very high off the ground. Down here, I'm not very high off the ground, but I'm moving a lot faster. So the amount of energy I have here and here is the same, but the amount of each kind changes because they turn into one another. Okay? Potential energy becomes kinetic as you go downhill and accelerate. Does that make sense? All right, so the formula for kinetic energy is this. Kinetic energy is 1/2 times the mass times v squared. Okay, so which has a bigger effect on your kinetic energy, mass or speed? Speed, because speed is squared. All right. If I was to double my speed, I would then have 4 times as much kinetic energy as I had before. If I were to triple my speed, I would have 9 times as much kinetic energy as I had before. It's an exponential relationship. Everybody with me there? Okay, it's important to remember that there is an exponential relationship between speed and kinetic energy, right? Because as a result, there's also a exponential relationship between speed and the amount of work needed to stop you. All right. So EK is the energy of the object. Obviously, energy is always measured in joules. M is the mass of the object, always in kilograms. V is the velocity. We should probably just say speed, okay, of the object, okay, in meters per second, right? And when we do that, when we multiply those things together, we get kilogram meters squared per second squared, which are joules. Okay. Now, how do we get kinetic energy? Where does it come from? Okay, movement, something we talked about last week. In order to have energy, you have to do work. Okay? The only way you have energy is if you've either taken in some other form of energy or you've had work done on you from a mechanical sense. Right? The same is true for getting rid of energy. If you want to get rid of energy, you have to do work on something else in order to transfer your energy away. Everybody follow me there? All right. So, best example of that, okay, and I'm just going to do it here. How many of you taken driver's ed already? Okay. Why do you suppose, other than the obvious reasons, the speed limit is lower in playground and school zones? Besides the obvious reason that there are children there. It takes longer to stop. The faster you go, the farther it will take you to stop. All right, now this is exactly what we've been talking about. That work is a change in energy. If you recall from last week, that is the work energy theorem. All right, now here's the example that I am going to show to you. Work is force times distance. Okay, we talked about that last week. Let's say I'm driving in a school zone and I'm driving the speed limit like I should. Okay, the speed limit in a school zone is 30 kilometers per hour. Okay, that is roughly 8.3 meters per second. Okay, so I'm driving in the school zone. I've got kinetic energy because my car is moving. Everybody okay with that? All right, now we're going to fill in some numbers here. I'm going to say that the mass of my car is 1,500 kilograms. And I'm going to say the force that my brakes can apply is 10,000 newtons. Okay, everybody with me there? And we've said I'm going the speed limit, so I'm traveling at 8.3, it's actually 8.3 repeating, meters per second. I want to solve for how far it will take me to stop. Okay, in order for me to stop, my brakes have to do work on my car. They have to take energy from my car and turn it into other forms of energy that do not involve me moving. What forms of energy do your brakes turn your kinetic energy into? Heat and sound. Okay? Heat and sound are the two forms of energy that your kinetic energy will be turned into. Now, two things can affect how far it will take you to stop. How big of a car you drive, your mass, and how fast you're going. Now we're going to assume it's my car in both situations. Okay? So I'm going to solve for D. How do I get D by itself? Not minus. If I want to move something, I do the opposite. I'm multiplying F right now, so I want to divide. All right, so I'm going to divide both sides by F. Okay, that's going to leave me with D. So now I can solve for how far it will take me to stop at the speed limit of 8.3 meters per second. All right, so 1/2 times the mass of my car, 1,500 kilograms, times the speed of my car, 8.3 squared. All right, and we'll say that's over the force, which we said was 10,000 newtons. All right, so plugging in those numbers. 0.5 times 1,500 times 8.3 squared. Okay, gives me 51,000. I divide that by 10,000. Okay, it's going to take me 5.2 meters to stop. Right? 5.2 meters is a fairly long way, really, when you think about it. If there's a kid running out in front of your car, 5.2 meters can be a long way. Okay? It's roughly the length of one row in this class. All right? Now, how fast do we usually go? If the speed limit is 50, we usually go 60, yeah, we all do it. Okay, everybody does it. We shouldn't. Okay, especially in a school zone or a playground zone, and I'm going to show you why. Okay, 40 kilometers per hour in meters per second is 11.1 repeating. All right, everybody with me here? I'm going to show you how much further it will take you to stop. Only going 10 kilometers an hour faster through this school zone. All right, so it's 11.1 meters per second now instead of 8.3. So now I'm going 40 kilometers per hour. Oh. Okay, so 0.5 times 1500 times 11.1 squared. $9.2. It's almost double. You're only going 25% faster, but it's almost twice as far to stop because the relationship between energy and speed is exponential. If you were to go 60 kilometers an hour through a school zone, it would require 4 times as much distance to stop. That's 22 meters, 21.5 meters roughly. Okay, if you went 60, it would take you 4 times as far to stop. Okay, now even going 10 kilometers an hour faster is 4 extra meters. Okay, almost twice as far. Okay, that is why the police enforce school and playground zones so strictly. Okay, they know the relationship between speed and stopping distance is exponential, and you don't have to be going that much faster to make a lethal difference in your stopping distance. Okay, that 10 kilometers an hour, guys, from a parent's point of view, is the difference between me going home and having to plan a funeral for a kid or going home and having dinner with my kid. Okay, it's a big deal. So the next time you think about speeding through a playground zone or a school zone, think about this. It's twice as far at only 10 kilometers faster. Okay? All right. Now, just a couple of things here. Which has more kinetic energy? A semi-truck traveling 30 kilometers an hour or a bicycle traveling 30 kilometers an hour? Ty? Really? Same speed. Same speed. Semi-truck, right? Semi-truck has more because it's heavier, it's bigger, there's more of it, okay? Mass makes a difference, okay? All right, water doesn't always freeze at 0 degrees. It sometimes sorry, I forgot to take that one off. That's about thermal. We're not going to talk about that till the next unit. Okay, yeah, we're going to skip those. Okay, we're going to go over a couple of these here, okay? These are examples of work energy theorem kind of questions that we might run into, okay? So I want you to quickly copy this one down, okay? And then we'll go through it together. Okay, so let's have a look at how we would solve this one. So if I stretch a rubber band by 0.85 meters using a force of 60 newtons, what speed would it propel a 0.125 kilogram ball when released? So essentially this is a slingshot question. Okay, you do work in pulling back the slingshot because you exert a force through a distance. You put elastic potential energy into that system. Okay, when you release the rubber band exerts a force on the ball through the same distance. Okay, and it turns that elastic potential energy into what? Kinetic. All right, so that's what we have to do. When we read a question, we've got to look at it and go, what kind of energy is changing in this question? Okay, right now, the kinetic energy, because it's talking about speed, the kinetic energy of the ball is what's changing. And that's changing because of the work being done on the system, which is the rubber band. Okay? All right, so work is a change in kinetic energy. That's the work energy theorem for this question. Okay, and we have our givens. All right, so distance is 0.85 meters. The force was 60 newtons. The mass of the ball was 0.125 kilograms. All right. Work is force times distance. And kinetic energy is 1/2 mv squared. But this is delta. What did we say delta meant last week? Okay, it's change, right? So that means the final kinetic energy, 1/2 mvf squared, minus the initial kinetic energy, 1/2 mvi squared. Now, we can simplify this a little bit. how much kinetic energy does the ball have when it is sitting in the slingshot? Chris? 0. Why does it have no kinetic energy sitting in the slingshot? It's not doing anything. It has no speed. All right. Therefore, this whole number then would equal 0. All right, because 1/2 times the mass times 0 is 0. All right, so we can get rid of that. That makes our formula kind of simple then. Okay, all we have to do is solve for V. All right, so how do I get V by itself? What do I need to do with the 1/2 and the m? Divide. Right. Okay, if I'm multiplying, I do the opposite. Divide both sides by 1/2 of m. Okay, that gives me Vf squared. Do I want V to be squared or normal? Normal. So what do I do? Square. Nope. Square root it. Right. Okay, because the square root of Vf squared is Vf. Okay. All right, so now I've got my formula. Now I just plug in my numbers. So the square root of 60 newtons times 0.85 meters over 1/2 times the mass, which was 0.125, okay, will give us Vf. Now, when you're punching this into your calculator, you have a couple of options. You can punch it all in at once, but you'll have to use brackets, or you can do it piece by piece. Okay, now, if you're going to do it with brackets, you really have to be mindful of how many brackets you're using. Okay, so this would be 60 newtons, the top, times 0.85, okay, divided by, right, the bottom, which is 0.5 times 0.125. All right, and you get 28.6 meters per second. Or you could do it piece by piece. You could just go 60 times 0.85 equals this, and then divide that by 1/2 of 0.125. That would still have to be in brackets. Okay, and then square root that. Right, you still get the same answer, right? You just don't have to keep track of so many brackets. Up to you how you would do it. All right, does that make sense? All right. Typically, guys, when you're doing a work energy theorem question, you're going to have force times distance is going to be equal to either potential energy, m times g times h, or it's going to be equal to kinetic energy, 1/2 mv squared. Right? And you're going to be solving for one of the things. To solve for those things simply involves dividing everything else over to the other side. Okay? It's not hard algebraically. Okay, does anyone need that anymore? Done? Yep. All right. I want you to copy this one down here, okay, and give it a try. Okay, and then I'll go over it with you in a few minutes. All right, so we've got this tractor pushing a rock that has a 550 kilogram mass from rest to a speed of 4 meters per second over a distance of 25 meters. What force is exerted? What kind of energy are we changing about the rock? Potential or kinetic? Is it moving any higher? No. Okay, so we're not changing its potential energy then, because we're not changing how far from the Earth it is. However, it is going from rest to 4 meters per second. I'm changing its speed. If I'm changing its speed, I'm changing its kinetic energy. Right. Okay? So the work I'm doing in this question is changing the kinetic energy of the rock, same as it was on the last question. Okay? So our givens are, okay, that the distance is 25 meters. Okay? The final speed is 4 meters per second. The initial speed is 0 meters per second, and the mass was 550 kilograms. Now, if my initial velocity is 0, what's my initial kinetic energy? 0. If I'm not moving, I don't have any kinetic energy. All right. So force times distance equals the change in kinetic energy, which means 1/2 mvf squared minus 1/2 mvi squared. And we've already said that since this is 0, all of that is 0. Okay, so I'm left with this, the same thing I was left with last time. It's just now I'm not solving for v, I'm solving for f. I'm looking for the force. Okay, so how do I get force by itself? What do I do with d? Divide it over to the other side. Right. Okay, so now force equals 1/2 mv squared. So force equals 1/2 times 550, the mass of the rock, times the final speed of the rock, 4 squared, over the distance traveled, 25 meters. Okay, so when we plug that in, 0.5 times 550, okay, times 16, which is 4 squared, okay, divided by 25. All right, so the force here is 13 newtons. Is that very much? It's not. Okay, you got to imagine this rock is on a frictionless surface in the perfect physical world, and it takes practically nothing to change the speed of something in a frictionless environment. All right, that's why astronauts in space can pick up satellites and move them around with their bare hands. Okay, their only problem is when they try to stop, they keep going. Okay, that can be dealt with. You're right. I don't square root it. I screwed up on there. Thanks for catching that. Absolutely right. That's why 13 is so small. Okay. Let's do that again. 0.5 times 550 times 16 divided by 25. That's a better number. 176 is still really small. Okay. 176 newtons is still puny. Right? Not as puny as 13, but it's still puny. Okay. Everybody with me there? To give you some idea, guys, on average, a human being weighs somewhere between 500 and 800 newtons. All right, so that force is like 1/8 or 1/6 of what you would push on if you stood on someone. Okay, so it's not a lot of force. Okay, is that making sense there, guys? What? Yes, but you guys are supposed to leave it 3. Okay. All right, try this one here. Now, when you look at this one, guys, we're not changing the person's speed in this one. In this one, the person's going up. All right, so we may not be dealing with the kinetic energy change. This time we might be dealing with a potential energy change. Okay, what kind of energy is changing here? Kinetic or potential? Potential. We're moving up. If there's a change in height, we're changing potential energy. All right. Now, our givens are that our initial height is 30 meters above the ground, and our final height, okay, is 100 meters above the ground. And it's, what do we got here? A 10 kilogram mass. All right. How much work is done? Okay. Work is a change in energy. Okay, and in this case, it's a change in potential energy. I don't need to put the force times distance in here this time. It doesn't ask me for either one of those. It only asks me for work. So all I have to do is subtract final potential energy from the initial from the potential. So that's going to be m times g times hf minus m times g times hi. Okay, work is a change in energy. Everybody follow me on that one? Okay, follow the reasoning there. I don't need force times distance. A, I wasn't given force or distance. Okay, and B, it never asked for either one, so I can just solve for work. So that's going to be 10 times 9.81 times the final height, 100, okay, minus 10 times 9.81 times 30. Okay. Now, I could probably also shortcut this and just go 10 times 9.81 times 70. That would be the change in height. Agreed? All right, but we'll do it this way because that's kind of the basic way to do it. Okay, so punch that into our calculator. Okay, 10 times 9.81 times 100. Everyone follow where I'm getting 9.81 from? Right, that's what little g is, the acceleration due to gravity. Minus 10 times 9.81 times 30. All right, so we get that the work done is 6,867 joules. Okay. Questions on that one? All right, so that's roughly what you would have, the work you would do if you had a 10 kilogram backpack and you went up 70 meters. Okay, that's how much work it would take. Okay, that would be the calories you would burn, generally speaking. Okay, so if you were like exercising, you're trying to figure out how many calories or kilojoules or whatever you were burning, okay, this is how you could figure it out. Alright, questions on that one? Okay, are all these essentially coming down to the same thing? Work is a change in energy. Okay, like I said, so the biggest thing you got to be able to do is figure out what kind of energy is changing, and then you're set. Alright, try this one. Okay, and you'll see that in this one, speed is in here, so we're not talking about potential, we're talking about kinetic. Okay, so one like this would probably be a little bit more on the challenging side. Okay, the other ones are pretty basic. This one here, you got to do a little bit more algebra kind of stuff for it. First, let's write down our givens. The first thing it tells us is the amount of work done. Okay, so we know that the work is 7,500 joules. Okay, and it says that it pushes the truck, which has a mass of 2,500 kilograms. Okay, from 2 meters per second, that would be the initial speed, to an unknown final speed. Okay, so is kinetic energy changing in this question? Yes, because the speed of the truck is changing. So work is a change in kinetic energy for this question. Now, do I have to plug in force times distance, or did they already tell me what work was? They already told me, so I don't need force times distance. Okay, all I need is that work equals the final kinetic energy minus the initial kinetic energy. All right. Now, is final speed part of initial kinetic or final kinetic? Final speed would be part of final kinetic, yes? Right? They're asking me here to find its final speed. Well, that would be part of this term here, yes? Okay, so if I want to get this by itself, what do I have to do with this? Not divide. What am I doing with it? I'm subtracting, so if I want to move it, I've got to add. Okay, so that's going to mean work plus the initial kinetic energy equals the final kinetic energy. Now that ought to make sense. Okay, if we think about it, work's a change in energy. So whatever I change the energy by plus what I started with should equal what I have at the end. Agreed? Okay. Now I can plug in numbers and formulas. They told me the work was 7,500 7,500 joules. Okay, and I can calculate the initial kinetic energy because I know the mass of the truck. Okay, and I know the initial speed of the truck, and I know that that equals 1/2 times 2,500 times VF squared. Okay, I want to get VF squared by itself. So what do I do with the 1/2 2,500? What do I do with this? If I'm multiplying them all together and I want to move those, I should divide it, right? Now here's where a lot of people make a mistake. They see 1/2 times 2,500 on the top and 1/2 times 2,500 on the bottom, and they go, I can cancel that. No, you can't. Okay, why can't you? No, I already divided the other side by 1/2 of 25. Right, I can't do it here because I've got another operation that this is involved in, so I can't cancel it. Okay, so there's my formula. That gives me VF squared. I want VF, so I square root it. So like I said, mathematically, this is probably the most involved one you would deal with. Okay, so VF then is going to equal, okay, well, we've already got it plugged in, so we'll just plug in the numbers here. Okay, so 7,500 minus 0.5 times 2,500 times 4. Okay, that's the top, okay, divided by 1/2 of 2,500. Okay, should give me 2, right? And then I take the square root of that. Okay. Oh, I messed something up somewhere. Did I forget to square something? must have messed something up when I punched it in. I minus, that's exactly what it was, yep. Yeah, I went minus up here. Sorry guys, I just pressed the wrong key up there. Thought that answer didn't look quite right. Okay, 7,500 plus. Okay, 0.5 times 2,500 times 4. That's better. Okay, now we divide that by 0.5. That's better, 10. Okay, gives us 10 meters per second as the final speed. Okay. Everybody with me there? All right, you're going to get time to practice this. Just like I said, this is the most important concept we take in physics. All right, so you're going to get time to practice this. If you don't get it today, it's not too big a deal. Okay. All right, so things to remember, and you're probably going to want to write this down because it isn't in your notes, but little tips. Okay, solving work energy theorem questions. Biggest thing, write out your givens. Okay. Work is always a change in energy, and usually you'll get a mark for writing that. So write out your givens, write out work is a change in energy, and you probably got 2 out of 5 marks already. Right? And you really haven't had to do any thinking yet. So that's a good deal. Okay? The next step, identify what type of energy is being changed. Okay, and I've said that in every single question. It's the first thing I ask you, what kind of energy is changing here? Okay, so identify, is it potential, m times g times h, or is it kinetic, 1/2 mv squared? Right? Then set up the work energy theorem. Okay, work's a change in energy. Okay, and your final minus initial. Okay, that could end up like either one of these. It could end up as force times distance equals final kinetic minus initial kinetic, or it could end up like this. Okay, then manipulate and solve, and you're done. Okay, so there's only a few steps, and those steps might come in handy. So I'll give you a minute to copy those down. All right, so for number 2 here, we're changing the height of it. So we're changing what kind of energy? Potential, right? As soon as we're changing height, we're changing m times g times h. Okay? We can't be changing 1/2 mv squared because we don't have any of that information. Okay, so work is a change in potential energy for this question. So force times distance equals m times g times h. Now it just so happens that for this one, the distance and the height are what? They're the same. You're lifting it directly upwards. If you're lifting it directly upwards, distance and height are the same. Okay? So I want to solve for force. I divide both sides by d. Okay? Boom. H and d will cancel because they're the same number. Okay? Everybody with me on that? And then I get force of gravity, m times g. All right, so I go 50 times 9.81 times 1.5 divided by 1.5, and I get 490.5 newtons, okay, which is the weight of that box. All right, questions on that one? Okay. All right, I want you to try this one. Okay, that is the answer there. Okay, so you can check your work as you go. Done. Yes. I know, because it doesn't matter whether I cancel them or actually whether I plug them in, makes no difference. They mathematically cancel away. Okay, so this one here, guys, is about as easy as they get in terms of a work energy theorem question for potential energy. All right? Work's a change in energy. Okay? In this case, potential energy, because we're pushing uphill. Okay? We're changing the height, we're not changing the speed. Okay? Force times distance equals m times g times h final minus m times g times h initial. What's your height at the bottom of the hill? 0. So what's m times g times 0? 0. So this you can get rid of. It's 0. All right. Can I solve for the final height of the box now? Okay. How do I get hf by itself? Okay. That's what I mean. How do I manipulate? What do I move? Divide by mg, right? All right, so when I do that, okay, and plug in my numbers, I'm going to have 150 newtons times 25 meters divided by 55 times 9.81. That'll give me hf. All right. Oh. What did I mess up here? Gotta check my work here, guys. Did I write something down wrong? 150. 35 kilograms, not 55. Can't read my can't read my own writing. I write things wrong. That'll do it. Instead of 35. That's better. Okay, so it's going to be 10.9 meters higher. And if you remember, last week we talked about how in a perfect physical world, pushing something up a ramp is no different than lifting something to the top of the ramp in terms of the change in energy or the work done. What is different is the force needed to accomplish it and the distance over which you would have to exert that force. If you're lifting something, lots of force, short distance. If you're pushing it up the ramp, less force, greater distance. Same amount of work either way. Alright, let's have you try this one here, and then we'll probably leave it at that. Okay, so give this one a try. Now, again, you've got here speed, so you got to consider what kind of energy is changing in this one. Okay, so in this one here, we're changing the kinetic energy of the ball because we're changing the speed of the ball. Okay, so work is going to equal the change in kinetic energy. Now, when a pitcher starts his windup, how fast is the ball moving? 0. So its initial kinetic energy is 0. Okay, so again, my change is final minus 0. We'll talk about that one tomorrow.